Welcome to oxidation-reduction reactions. So, let's examine the reaction between sodium metal and chlorine gas. So we have sodium metal reacting with chlorine gas. Now, in this case, because the chlorine is diatomic, we need two sodium atoms reacting with the chlorine molecule to give us two sodium chloride molecules or formula units. In this case, it's a solid. So in this reaction, each chlorine atom takes an electron from a sodium atom, and this results in a sodium ion and a chloride ion that then form an ionic compound with one another. So this is an oxidation-reduction reaction, and we generally abbreviate this as redox reaction. So this is a reaction in which one or more electrons are transferred. So to discuss redox reactions, we must introduce the concept of oxidation states. So an oxidation state, or oxidation number, is an indicator of the degree of oxidation of an atom in a chemical compound. So the oxidation state is the hypothetical charge that an atom would have if all the bonds to atoms of different elements were 100% ionic. Now, they're not. In fact, they're not 100% ionic even in ionic compounds, but we're assuming here that all of the bonds are ionic in order to assign full oxidation states, full charges, as they were, to all of our atoms. And so something like water, we're assuming that the oxygen-hydrogen bond is completely ionic, even though it's really not. Right? We really have a partial negative charge on the oxygen and a partial positive charge on the hydrogen. But here, to calculate oxidation state, we're assuming that that's 100% ionic. The hydrogen has an oxidation state of +1 because it's going to lose the electron because the oxygen atom is more electronegative. The oxygen atom would have a charge of -2, or an oxidation state of -2, because it's bonding to two hydrogen atoms. So the oxidation state, again, is our hypothetical charge that the atom would have if all bonds to atoms of different elements were 100% ionic. So this means that we have to examine the Lewis dot structure and assign shared electrons to one atom or the other. The more electronegative element is assigned both electrons in a bond. If we have identical elements, so that's why we have atoms of different elements. If atoms were the same element, so if we have an oxygen atom bonded to another oxygen atom, then each element gets one of the two electrons. So if the atoms are of the same element, then they share the electrons equally. So one electron goes to one atom, the other electron goes to the other atom. In the case of, say, oxygen, where there's a double bond, each oxygen atom gets two electrons. So oxidation states can range from -4 to +8. This is in general. There are a very few numbers of cases where they range outside of these values. So the oxidation states of a compound or a polyatomic ion must add to give the overall charge. So 0 for a compound and the charge on the polyatomic ion in the case of an ion. So note that technically the oxidation states are written with the sign first and then the number. So in the case of water, it's H2 +1, O -2. And in the case of NO2, it's N +4, O2 -2. And the charges are written with the number first and then the sign. So in sodium oxide, the sodium ions have a charge of 1+. Note that the hydrogen up here was +1, not 1+. And the oxide was 2-, whereas up here the oxygen atom had an oxidation state of -2. Down here it has a charge of 2-. And down here in nitrate, in the NO3-, we have an overall charge, so a charge on the whole parentheses there of 1-. The nitrogen has a charge, or rather an oxidation state of +5. If it had a charge of +5, it would be 5+. And the oxygen atoms have an oxidation state of -2. Again, not a charge, because that would be 2-, like up here in the oxide. So, there's a difference between oxidation state and charge. Charges, again, are written number first, then sign. Oxidation states are written sign first, then number. So, oxygen is more electronegative than hydrogen, so the electrons in each oxygen-hydrogen bond are assigned to the oxygen, and this means that the oxygen has an oxidation state of -2, and each hydrogen has an oxidation state of +1. In carbon dioxide, oxygen is more electronegative than carbon, so the electrons in each carbon-oxygen bond, that double bond, are assigned to the oxygen, and the oxygen atoms thus have oxidation states of -2, and the carbon atom has an oxidation state of +4. Now note that they don't actually have charges of +4 or 4+ and charges of 2-. These are oxidation states, because we're assuming here, now we're wrong in that assumption, but we're assuming here, in order to make some math work out, that those bonds are 100% ionic. Now they're not ionic. But, so, in sulfur hexafluoride, we have the fluorine atom is more electronegative than the sulfur atom is, and so the electrons in each sulfur-fluorine bond are assigned to the fluorine atom, and this means that the fluorine atoms each have an oxidation state of -1, and the sulfur atom has an oxidation state of +6. In the nitrate, again, we already saw this earlier, but let's look again. So the oxygen is more electronegative than nitrogen is, and that means that each of the electrons in each of the nitrogen-oxygen bonds are assigned to the oxygen atom. This means that the oxygen atom has an oxidation state of -2, and then the nitrogen atom has an oxidation state of +5. Note that in some compounds, the oxidation state of an atom is not an integer value. So the oxidation state of each of the 4 oxygen atoms in iron oxide here, this is iron 3 oxide. So again, the oxidation state of the oxygen atoms is -2. This means that the total negative charge is -8. The total positive charge has to be +8 because this is a compound, so we have no overall charge. And this +8 charge has to be divided evenly amongst the 3 iron atoms. But we have now +8 divided by 3. So we have an oxidation state of +8/3 for each iron atom. Now that's okay. We don't have to say, well, we don't have to assign integer values to each of the 3 iron atoms, right? We don't have to say that, well, 2 of them have a charge of +3 and 1 of them has a charge of +2. We don't have to do that, right? We can say that they each have an oxidation state of +8/3. So let's examine the reaction between methane and oxygen. So here we have methane, CH4, plus oxygen yields carbon dioxide and water. So the oxidation states for the carbon atoms, or for all of the atoms, the carbon in the methane is -4. The hydrogen in the methane is +1. The oxygen in the oxygen molecule is 0. The oxygen in carbon dioxide is -2. The carbon in carbon dioxide is +4. The oxygen in water is -2, and the hydrogen in the water is +1. So you can see that the carbon there has gone from a -4 to a +4. So has it gained or lost electrons? It's gone from a negative charge to a positive charge. That difference is 8. So theoretically, at least, it's gone from having 4 extra electrons, because remember, electrons are negatively charged, to having 4 fewer electrons than it does in the elemental state. So it went from having extra electrons to having fewer electrons. That means it had to lose electrons. Let's see, hydrogen started out as +1 and it ended up as +1. The oxygen started out at 0 and ended up as -2. So the oxygen atoms have gained electrons, at least theoretically here. They've theoretically gained electrons. The carbon has theoretically lost electrons. The hydrogen has done nothing. It hasn't gained or lost any electrons, so it's unchanged. So, note that while no electrons appear to be transferred, right, we don't have any charges that are changing here. The oxidation state of the carbon atom is increasing, it's becoming more positive, and the oxidation state of the oxygen atoms is decreasing, it's becoming more negative, and the oxidation state of the hydrogen atom is not changing. So, oxidation, then, is an increase in oxidation state. This means that we have to be losing electrons, like the carbon was. Reduction is a decrease in oxidation state, which means we have to be gaining electrons in order to lower the oxidation state. And we can remember this by Leo the lion GERS. So Leo is lose electrons, oxidation. And GERS is gain electrons, means reduction. So if you're losing electrons, that's oxidation, Leo. And he's GERing, he's growling. Gain electrons means reduction. So an oxidizing agent, or an electron acceptor, is the species that's oxidizing the other reagent. So note that in the process of oxidizing the other reagent, the oxidizing agent has to get reduced because it has to gain electrons. Because remember, the species that is being oxidized is losing electrons, it's giving up electrons. Well, those electrons have to go somewhere, they're going to the oxidizing agent. The oxidizing agent then is gaining electrons, that means it has to be being reduced. So the reducing agent, this is the electron donor, the one that's giving up the electrons. This is the species that's reducing the other reagent. So again, in the process of reducing the other reagent, the reducing reagent is getting oxidized because it's losing electrons. As it loses electrons, as it reduces the other reagent, it's giving up electrons. As it gives up electrons, it's getting oxidized. Its oxidation state is getting more positive. So, let's return to our methane oxygen example, and now in this case, oxidation states have been added. So, what's being oxidized? What's being reduced? And what is the oxidizing agent? And what is the reducing agent? I'm going to pause the video and figure out what is the correct answer to each of these questions. So, what's being oxidized? Remember, the thing being oxidized is the species that's having its oxidation state become more positive. So, the carbon, remember, started out as -4, it ended up as +4, so the carbon is being oxidized. So what's being reduced? Well, the oxygen started out with an oxidation state of 0, it ended up with an oxidation state of -2, so the oxygen is being reduced. So, what's the oxidizing agent? This is the thing that is oxidizing the other stuff, the other reagent. The carbon was being oxidized, so it can't be the oxidizing agent. It's being oxidized. So what is oxidizing the carbon? The oxygen. So the oxygen atoms are oxidizing the carbon. This is why we call it oxidizing, because oxygen is a very good oxidizing agent. So the oxidizing agent is the oxygen. The reducing agent is the carbon, because as the carbon gets oxidized, as it gives up its electrons, it's reducing the oxygen. So that was oxidation-reduction reactions, redox reactions.